Morning, sir. My name is Prishaya from EC Department B section, and my TikTok topic is Coulomb's law discretization method, a new methodology of the radial point interpolation method. So, introduction. The importance of the meshless or the mesh-free methods has been expressively rising since they enable the accurate numerical representation of non-rectangular geometries with no need of meshes for solving partial differential equations. These methods emerged in 1977 with the smooth practical hydrodynamics SHP, the first meshless method formulated to solve the astrophysics problems. Therefore, the following methods were proposed: the produce kernel practical method RKPM and the corrected smooth practical hydrodynamics CSPH, which presented several improvements over the SPH method. Subsequently, the based on the MLPG and Liu and Yu developed the point interpolation method PIM. In 2000, Wang and Liu introduced the radial PIM, RPIM, a method based on the PIM and on radial basis functions. In 2009, RPIM was applied for solving Maxwell's equations in 3 dimensions. In 2011, Machado and Oliveira published a new method called local shape factor calibration method LSFCM for improving numerical precision of interpolations by calculating optimized shape factors for each support domain. The meshless methods are so called because the analysis space is discretized by means of the node group domain where there is no predefined element schema as in finite element method FEM or cell formulations. The influence that the nodes in the exert on each other is accounted by using a substance of a neighboring nodes. The support domains denoted by for the each node Z bar is this way, the complicated problems related to meshing process cease to exist. A natural thought that is that for meshless method analysis domain can be represented by a set of randomly distributed nodes. This is true provided that discretization quality parameters are satisfied and the counters and relative to the problem are represented accurately, requiring specialized methods for of spatial discretization and the other approaches have been developed, but the most notorious methods are based on the Voronoi diagram and triangulation. In this context, the main objective of this paper is to present a simple and however effective and auto-adaptive measures to spatial discretization method based on the analytic dynamics of Coulomb's law to generate the node distribution for analyzation domain. The proposed method is named Coulomb's law discretization method CLDM in the work, and it is not associated to any traditional meshless technique. The theoretical background. The radial point interpolation method RPMI, the basic principle of meshless methods is to obtain an approximation f of x bar for function of interest f of x bar. For each method, each node, Z bar belongs to the node by using the radial basis functions and samples of Z bar on the neighbor nodes J and around Z bar. In order to solve the differential equations, approximations for the derivatives of f of x bar are also of interest. The general radial basis function cannot shape every kind of function, so a polynomial base is included. This way, the approximation f of z x bar may be defined as f of x bar equals to the summation I tends to 1 to n r of I x bar ai plus summation j equals to 1 to m and p of j x bar bj, which can also be written in the matrix form as f of x bar equals to r bar t x bar a plus p bar t x bar b. So where r bar t x R party of x bar is equals to R1 x bar and R2 x bar, so on. Rn x bar is the matrix of radial basis functions A equals to A1 to An part T are the coefficients of the each radial basis function, whereas P of T P bar T x bar is equals to P1 x bar, P2 x bar, so on. Pm x bar is the vector of polynomial basis B equals to B1, B2, so on till Bm bar T are the coefficients of each polynomial term. N is the number of nodes in the SR of x bar and m is the number of polynomial terms. If the two-dimensional problems are considered, x bar equals to x comma y, p bar t of x bar equals to 1 comma y comma x comma y and y square xi x squared, so on till m, and the rj of x bar equals to e bar c by r square max into root over x minus xj whole square plus y minus yj whole square and whole square, where r max is the radius of x bar and the xj equals to xj comma yj is the jth node in the x bar and c is the known as the shape factor. The vector of the polynomial basis p bar t x of x bar is usually considered to be the p bar t of x bar equals to 1 comma y comma z, sorry 1 comma x comma y. The RPM applied to the Maxwell equation. Maxwell equations are the set of partial differential equations that describe the physics associated to the electromagnetic wave propagation. In this work, it is used the TMZ mode in the regulator coordinates, where the Maxwell equations in the 2D can be written as derivative of Ez equals to 1 by epsilon naught into derivative of xy with respect to x and hx derivative with respect to y. The expressions 1 to 4 can be written, can be used to construct so-called shape functions. Phi of x bar equals to phi of 1, phi of 2, so on till phi of n, specific for each support domain, as described in such a way that f of x bar equals to epsilon j equals to 1 to n and f of j x bar phi of j x bar. The spatial derivatives of the field's components can be obtained by computing the phi of j and phi of j with respect to x and y. This way, phi to 7 can be approximated by e power nt plus 1 zi equals to e power nt zi, where the t equals to nt into delta t is the time in seconds and delta t is the rpm im times step, and I is the index of the node space at the z bar. It must be emphasized that in this work n ranges from 8 to 16 according to the considered support domain. The radii of all the support domains are approximately equal. The maximum distance from x bar to x day for all x day. In this work, the factor of polynomial basis has been modified to ensure independence in the interpolation coefficient on x bar, such that p bar t of x j bar equals to 1 comma x j minus x and y j minus y. In order to truncate the analysis space, the uniaxial perfectly matched layers UPML formulation has been employed for observing the fields at the limits of the standard procedure for the treating open problems. It is also noteworthy that the Gauss's law are automatically satisfied by Faraday's and Ampere's equation when written in the rectangular coordinates. Coulomb's law and analytical dynamics. The Coulomb's law reverse square law is seen today as a classic law of electrostatics developed in 1785 by Charles Coulomb. This law describes that the electrostatic force interaction between electrically charged particle, and it was essential to the development of electromagnetic theory as it builds the foundation of electric field concept. The Coulomb's law states that the magnitude of the electrostatic force F resultant of the interaction between 2 point charges Q1 and Q2 is directly proportional to the scalar multiplication of the magnitudes of charges and inversely proportional to the square of the distance r between them. The electrostatic force F promotes the attraction if the two charges are with the different signs. Here we can see the figure of Q1 and Q2 with the different signs, plus minus, minus minus, plus plus. So when the Q1 and Q2 have the opposite charges, they attract each other, and when they have the similar charges, they repulse. Figure 1, the force is produced by the electrically charged particles. After detailed experiments, the Coulomb found that the force produced by the charge Q1 acting on the charge Q2 in the free space is completely described as a factor by F12 equals to 1 by 4 by epsilon naught into Q1 by Q2, Q1 Q2 by R1 R2 cube into R12, in which the R bar 12 equals to R2 minus X2 minus X1, where Xi is the point vector defining the position of the Qi in space, and epsilon naught is the electric permittivity of vacuum. Coulomb's law is usually described for the system of two charges. However, it is widely known that this total force, the resultant force on the test charge Qi produced by the set of n point charges Q1, Q2, so on till Qn, is given simply by the vector sum of forces related to each other of n charges, principle of superposition. Mathematically, one has Fri by it equals to sigma j1 to n f bar ji, where j is not equals to I. By applying the Coulomb's law and the principle of superposition to a system of four identical point charges in which the charges Q1, Q2, and Q3 are spatially fixed at the vertices of the equilateral triangle, and Q4 is free to move over space, it can be seen that if charge Q4 is positioned outside the triangle, figure 2a, and the force F4, the resultant of the forces acting upon Q4 pushes the Q4 away from the triangle. However, if Q4 is positioned initially inside the triangle, the resultant force drag R4 bar charged Q4 is to be centered of the triangle. Figure 2, analytic dynamics applied to a system of four particles with the same charge. Q4 is the only particle free to move over space. With no laws in generality construct this two-dimensional space, the case in which there is an infinite set of movable particles, all with same electric charge in force equilibrium state, notice that the charges must be equivalently positioned. However, if a charge Qi is moved and remain fixed at any position other than its original equilibrium location in the set, the system of particle reacts in order to produce a new equilibrium state due to the new location of Qi. As far as Qi is fixed at the new locus, the other particles tend to move and a new equilibrium state is established in such a way to satisfy the principle of minimum total potential energy, as it is established by the analytical dynamics due to the second law of thermodynamics. This effect is the basis for the discretization method proposed in this work. So the figure 3, two-dimensional analytic dynamics applied to an infinite set of charges. A is the initial equilibrium state, and B is the displacement to a single charge, and C is the new force equilibrium state. Coulomb's law discretization method, CLDM. Consider a set of movable charged particles. If the principle of minimum total potential energy is not satisfied at the given time t, then every movable particle is pushed by each other simultaneously in such a way to minimize the resultant forces acting on every particle. Now consider movable charge particle Pi placed initially at xi within the set. As illustrated by the figure 3 in this context, according to the Newton's second law of motion, the resultant force Fr I bar acting on the particle Pi can be written as Fri bar equals to ms into Ai bar, in which ms is the mass of Pi and Ai bar is its acceleration F equals to ma. By two-dimensional analytical dynamics applied to the infinite set of writing in terms of the particle's velocity Vi, one gets Fra equals to ms into A equals to ms into derivative of Vi with respect to time. And by using finite differences, assume that the form Fra equals to ms into Vi minus Vi par t in t minus t naught, which is a Va minus u by delta t, where Fi bar is the resultant force on the Pi the time t, and Vi is the velocity of Pi at Vi t minus delta t, and t delta t is the CLDM time step. By using finite differences, the position xi of Pi is associated with two particles' velocity by xi minus xi bar by delta t equals to Vi. In this presentation, it is assumed that ms equals to 1 for all. The vector spatial step is given by Fri bar delta t by ms plus Vi, where is the absolute distance among the particles at t minus delta t. V maximum modulus is the maximum absolute particle velocity in at t minus delta t, and the factor constant that assures stability to the maximum, which is gamma, determined to be the gamma is greater than or less than 10. Notice that the delta t is unrelated to RPMI time step. Conclusion. In this presentation, a messless discretization method called Coulomb's law discretization method CLDM is introduced, and the method is based on the Coulomb's law, and the virtual charges are used to perform the spatial discretization. Basically, two groups of particles are set of movable and unmovable charges. Unmovable particles are used to describe interfaces among different media to stimulate it and create a border region for avoiding particles to dispersed from analysis domain. Movable particles are employed to create smooth and transitions on discretization among the various objects immersed in space. The particle accommodation process, which produce force balance among the particles, is obtained naturally by using Coulomb's law analytic dynamics. CLDM was applied successfully to problems involving electromagnetic scattering and the PBG filters with complex geometrics. High accuracy is observed for CLDM, SLFCM, RPM when analytical solutions are used as reference because meshless geometric representation is conformal. However, the stability problems are presented by RPMI under these conditions, and further research is suggested for super improvements. Thank you.